Okay, so we rushed through some of these optimization problems last time. I just wanted to do a bird's eye review of the things that we solved using our calculus techniques. So I don't want to go through this so much, but this is a summary of what we learned about how to find maxima and minima. You just write down a function, look at critical points, the endpoints of an interval, and places where the derivative is undefined, and pick the max and min, the largest and smallest outputs. So we've done that many times now. I gave this sort of cookbook when you're given a context-rich problem, like some, problem with a diagram that's not obviously related to a calculus problem. You write it in terms of a function, eliminate variables using constants, and then apply the arguments of the previous slide, where you find all the points in those three classes and compare their outputs. So then we saw a few ways of doing that. There was this nice Snell's law problem where we needed to minimize travel time for a beam of light. So we did that by, assigning kind of letter values to the points P, O, and Q, and then using those to write down the time it takes for light to travel from P to Q, and then we minimize that function. So we saw that answer last time. We got this nice function by Pythagoras. We looked for critical points, and then we re-expressed this in terms of angles to get this Snell's law thing. So that was the first nice result. Then we had this problem about a garden. So the garden told you that the area had to be fixed. So that was, as we saw, it ruled out theta equals 0, because that would give you 0 area, which would contradict the fixed area. Then we were asked to minimize the perimeter, the length of the fencing, given that the area is fixed. So to do that, we had to eliminate some variables. We wrote down the area, and then said the area was, we wrote area in terms of theta and r, said area is a constant. So we used that to eliminate one of the variables, in this case r, by substituting in for this formula in terms of a constant. We got a function of one variable theta, which we extremized by taking the derivative, and then got the minimum. It was another nice problem. Then we had this ladder problem. So we saw that if you're carrying a thin ladder, so a ladder which has length but no width, around a corner, kind of the limiting factor is this bottleneck, where you have to think about just the length of the ladder. So we discussed an interesting generalization where if you're carrying around like a sofa or something which has area, then you need to think about the area of this bend. But for the ladder, which has only length and no width, you don't need to think about the area, you just think about the dimensions of the hallway, A and B. So it took us a while to work through that, but first we wrote down the sort of minimum length of the corner to corner distance in the hallway. So to do that, we said if you were at a given kind of length and width along the hallway, so to speak, x and y, what is the ladder that could fit through there? We wrote that down by Pythagoras, and it gave us something like this, although I think we did it slightly differently last time, because I didn't split it into two terms. I think you suggested writing the whole length of the ladder at once, but we still got the right answer. Then we eliminated a variable using some trigonometry, that b over x is y over a. And then we had to do some calculus, so we took some derivatives and found the minimum. And as we correctly found, the minimum for x was this a to the 1/3, b to the 2/3, and then you have to plug that back into the formula for the length of the ladder to get the smallest ladder that could fit through the hallway. And it gave us this nice formula, these nice powers that cancel perfectly to give us units of length, meters. So, okay, that's the big picture review from last time. Thoughts or questions on any of that stuff?
Nothing on any of this, but an amusing thing that just happened.
Oh, tell me the amusing thing.
I looked in my trash can and saw that the box of the breadboard says over 5,000 insertions.
Wait, sorry, you cut out because of push to talk. It says 5,000 what?
Over 5,000 insertion cycles.
Two comments. One, it would be better if it were over 9,000. Two, that sounds, yeah, pretty sexual. Good. Other comments?
No productive comments.
Any unproductive comments? I enjoyed that comment, I must confess.
Nope.
Okay. All right, let's do new things. Oh, wait, sorry. Before the new thing, one other comment about this ladder problem. There's a different way of solving it, which I don't like as much, but instead of optimizing over x, the horizontal distance, you could have instead written the angle, this thing. Yeah. You could have said, I'm going to make this the one variable that I extremize with respect to and use theta instead of x. And actually, this is the way the AOPS book does it. I don't know, the solution seems very inelegant to me because you have to use these really ugly trig identities at the end, like secant of tangent inverse and cosecant of tangent inverse. So I don't like their solution as much, but you get the same answer, the 2/3 and, 2/3 plus 2/3 to the 3/3 thing, so 3/2. So, I don't know, just a side comment that it's a matter of taste which variable, x or theta, you prefer to use in your extremization, but I like the x better, personally. Okay, a new thing. Well, I don't want to bias you, so I will just give the spiel, and then we can discuss how these problems are presented later. But the idea will be to consider some dynamical system, so something which is changing in time, and try to find constraints on configurations of that system. Okay, so that's very abstract. What do I mean by that? So suppose I hand you a description of a physical system, and I tell you it's changing in time. So to emphasize it changes in time, we call it dynamical system. So dynamics means changing in time. Now, if you have some equation, like a constraint, often a geometrical constraint, which this physical system must satisfy at every fixed time t. So, I don't know, we'll have an example with a balloon, but this could be, some relationship between the volume and radius, for instance, and that equation doesn't involve time explicitly, but you know that the system must obey that equation at every fixed time. So that will be our constraint. The observation we're making here is that you can get additional data about the behavior of this dynamical system by taking that equation you have which holds at one time, a fixed time t, and taking the time derivative of that equation. So you will take the left and right derivative, of each side, the derivative of the left side and the derivative of the right side with respect to time, and this will give you a new equation which the system will also satisfy, and this often tells you more interesting stuff about the system. Okay, so that's all very abstract. Let's pick a very specific example. So I have a balloon. For simplicity, we will say the balloon is a sphere, even though balloons tend not to be spherical. But suppose we're inflating a spherical balloon, and we know by geometry that at every fixed time t, so if I just freeze frame and look at the balloon at some time, I know by geometry that the volume of that sphere is 4/3 pi r cubed. The difference now is that we're inflating the balloon, so volume and radius, I'm going to try to put in little parentheses here, but volume and radius are now changing in time. Right, if I inflate the balloon, the volume gets bigger, the radius gets bigger, but at each fixed time, they satisfy this relationship. So the clever physicist looks at this and thinks, well, okay, this is true at every single time, so it must be true that if I take the derivative with respect to time, I get another correct equation. So if I take the derivative of the left side with respect to time, I simply get dv dt. If I take the derivative of the right side with respect to time, we have to be careful because r of t is now a function of time, so we need to use the chain rule. So just to be explicit, the time derivative of r of t cubed when r depends on time by the chain rule, well, the outer function is something cubed, so the derivative is 3 times that thing squared, and the derivative of the inner function is just dr dt. So when I use that in this equation, the 3's cancel, and I get 4 pi r squared dr dt. Okay, fine. I mean, I've written that equation here. I'm a physicist, so I like to use the dot, the over dot, when we're taking time derivatives. So instead of dv dt and dr dt, I write v dot and r dot, but it's the same equation. Okay, perhaps obvious or perhaps confusing. So thoughts or questions on this?
I see nothing special about this thus far.
Okay, good. Me neither. Glad you agree with me, because high school calculus courses seem to think this is extraordinarily special. But okay, let's just put some numbers on this. So I'll reproduce the equation from the previous slide. That's a very bad dot because my pen screwed up. V dot is 4 pi r squared r dot. Man, my pen is skipping today. There we go. Okay, so let's put some numbers into that example. So suppose I'm pumping air into a balloon. So I'm inflating the balloon at this rate, 2 cubic centimeters per second. And now I say, at a particular snapshot, at a particular instant in time, the radius of the balloon is 3 centimeters, and the volume is increasing by this 2 centimeter cubed per second rate at which we're pumping air in the balloon. And I ask you, how fast is the radius increasing? What is the time rate of change of the radius? So what should I do to solve this problem?
I'm almost inclined to believe that it is reasonable to just insert these variables in.
Okay, good. So which
Is
one
the
of those?
derivative? What? So we know that the radius is equal to 3 centimeters. But 3 centimeters squared isn't a thing.
Well, okay, let's go one by one. So you say the radius is 3 centimeters. So this
Yeah.
is 3 centimeters quantity squared. Okay, what about v dot and r dot? What do we do with those?
Thinking. How simple is the answer?
It's just a number, man. it's pretty simple.
It's just a number. Okay. I guess 3 centimeters of time?
Well, let's write the next line of the equation correctly first. So, what's v dot and what's r dot in what we're doing? So one of these is known, and one of these is what we're trying to solve for. So, which is which, and what should I write for the known one?
I believe we are trying to solve for v dot. Excuse me, no. R dot.
R dot. We're trying to find the
Correct.
radius time rate of change. So, r
Right.
dot I'll leave as a variable. What do I put for v dot?
Oh, this is going to be 4/3 pi radius cubed, and radius is equal to 3, to my knowledge. Since we know that.
No, that's v.
Oh.
4/3 pi r cubed is v. This is v dot.
Okay. Oh, that top equation. Okay. Volume with respect to time.
Yeah, how fast is the volume changing with respect to time?
Oh, is it 2 centimeters cubed per second?
Yes.
Wow.
Yeah, so this is just, I mean, the intuitive picture is if I have the balloon and I have some, pump attached to it, and I'm telling you that the air is flowing through this pump at the rate of 2 cubic centimeters per second, well, every tiny parcel of air in this pump eventually enters this balloon. So the volume of the balloon must be increasing at the same rate as we are pumping air into it, right? So v dot, the change in volume of the balloon with respect to time, must be the same as the airflow rate, 2 cubic centimeters per second. So indeed, as you say, the left side is 2 cubic centimeters per second. Okay, so let's solve this for r dot. Now, what do we get for the time rate of change of the radius?
Just by algebra, this is going to be 2 centimeters cubed per second all over 4 pi 3 centimeters squared.
Yeah, so 4 pi, I'm going to square this, so that's
Yeah.
9 centimeters squared. And now let's simplify. We cancel centimeters cubed with centimeters squared, which leaves one factor of centimeters upstairs. Cancel a 2 with a 4 to leave a 2 downstairs. And I think this gives us 1 over, let's see, 2 times 9 is 18 times pi is 18 pi. So that's the numerical part. The unit part is centimeters per second. Okay, good. Let's do a sanity check. Does the dimension, do the units make sense? Well, r dot is how fast is a length, the radius, changing with respect to time. So the unit should be length per time. Centimeters is length, seconds is time. Alright, good. Does this part make sense? Well, it's a dimensionless number, so that's a good start. I don't have a good intuition for how big this number is. It's about 1 over 60 or something, so it seems sensible, but it's hard for me to do answer analysis on the size of the actual rate of change. So, I don't know. I'm satisfied with this. It ends up being the correct answer, so looks like our calculation has worked out. Thoughts or questions on this part?
I have no thoughts or questions.
Okay, let's do a somewhat more painful example. Well, first let's make sure we got the right answer. Yes, v dot is 4 pi r squared r dot. 2 centimeters cubed per second is 4 pi times 3 centimeters quantity squared r dot. And as we saw, we can solve and get this thing, centimeters per second. Okay, so that sounds good. Let's do a somewhat more involved question. I took this out of the AOPS book, which you can tell because it has a somewhat annoying focus on checking whether you're paying attention to stupid details. One of those stupid details is that they give you one length in kilometers and another length in meters. I don't know why that's useful, but let's pay attention since that's what they seem to be suggesting we do. So with that in mind, we're talking about an observer who's 1 kilometer away from a launch pad. So I'll draw this like this. We're kind of viewing from the side. Here's the observer in the bottom left. Here's the launch pad in the bottom right. The observer is 1 kilometer away horizontally, so I'm going to put in a 1,000 meters here, doing the unit conversion right away. Now at time t equals 0, we're told that a rocket starts from this launch pad and starts moving upwards. So the rocket starts moving upwards, and now I've drawn this picture at some later time t. We're told that the rocket achieves an altitude, so that's this vertical distance, an altitude of 10 t squared meters at a time t. And then we're asked, okay, 5 seconds after takeoff, so when t equals 5, how fast is the distance between the rocket and the observer changing? So by distance between rocket and observer, I don't mean the horizontal distance, I mean this shortest path distance d of t on the hypotenuse. How fast is that changing? Which means we're looking for d dot, right? The rate of change of d with respect to time. Okay, so first a question for you. Since we're trying to solve problems that involve taking the derivative of some equation which holds at every fixed time, let's start with that. So looking at the picture, what equation do we have at a fixed time, just by some geometrical argument, which must hold and must relate the quantities given in this problem?
By the man, the myth, the legend, Pythagoras.
Good. What does
We
Pythagoras
see
tell us?
that desperately trying to remember things. That d of t is going to be equal to square root of 100 plus 10t squared meters, quantity squared.
Yeah, 10 t squared meters. quantity squared. Okay, good. A small trick. This is correct. We can take the derivative of both sides and proceed. I hate taking the derivatives of square roots, so I'm going to just, as a trick which is often helpful in these problems, I'm going to square both sides. So we know d squared is 1,000 meters squared plus 10t squared. I'm going to start dropping the units in the next line, but for now this is still meters squared. The reason I write it this way is because it's easier to take the derivative of the left and right sides of this equation when they only involve powers instead of square roots. So both are fine, but I like the easier one. Okay, good. So let's take the time derivative of the left and right side of the squared equation. What do I get on the left, remembering by the chain rule that d depends on time?
I believe we see by the chain rule that this is going to be trying to remember d of t, excuse me, 2d of t times d prime or d dot, however you would.
I'm putting d dot. I like it. I'm also going to suppress the d of t's. Everything
Right.
depends on time, so that's fine. You could write this as d of t, d prime of t if you like, but I'm going to pull some physics shit. Okay, what about the right side?
The 100 meters quantity squared is equal to 0 since it's constant. And this is added to, well, we've got some chain ruling and product ruling to do here. So this is going to be equal to 2 times 10t squared meters times thinking 20 t meters?
Yeah, 20t. I'm dropping all the meters because I'm getting lazy, but what you said is correct. So indeed, 2 dt dot is twice the quantity 10 times squared times 20t, the derivative of the inside. Okay, so the first intermediate result we get by solving for d dot, right, because we're interested in how fast the distance is changing. So I'll divide both sides by a 2d, kill this 2, and on the right side we get 10t squared times 20t upstairs, because I've killed the 2. Downstairs we get a d. Okay, so this is good, and now I will tell you why I don't like these problems. For some reason, AP Calculus courses like to assign a lot of problems of this form, which they assign the gimmicky name related rates. I don't like that. Related rates sounds like a stupid name to me. And my objection to these problems is that the problems typically require only one step that actually involves any calculus, which we've just done, taking the time derivative, and then the rest of it is an algebra or geometry problem. So I will we'll finish the rest of the problem just for the sake of being methodical, but from now on there will be no calculus involved whatsoever. It's just going to be using geometry and algebra to get a numerical answer for d dot at a particular time. So, I don't know, you can turn off your brain from now if you like, but okay, I'll erase all of the calculus that we've just done. Now we have this nice equation for d dot. And I'll ask you, now that we have this equation for d dot, we need to evaluate this at 5 seconds after takeoff. So there's two things to do. We can plug in 5 seconds for t just fine. That's easy to do. But how do we find the denominator? How do we find d, which is the distance between the observer and the rocket, at 5 seconds after takeoff?
Can we just plug it into the equation we generated?
Which equation?
The square root of 100 meters squared plus 10t squared quantity squared.
Yeah, so 1,000 meters squared plus 10t squared. When t equals 5, that's what, 10 times 5 squared, quantity squared, right?
Right.
I should put meters in, but I'm getting lazy. I despise this part of the problem. Um, this problem, by the way, is assigned with the expectation that you're solving it without a calculator. So at this step, you have to be a little clever, and you say, how do I simplify this expression without a calculator? Well, you say, okay, 1,000 is 250 times 4. Why did I do that? Because the second term, 10 times 5 times 5, 5 times 5 is 25, so 10 times 25 is 250, right? So the second term under the square root is 250 squared. Now the trick is to notice that there's a 250 squared, by the way, by the square, in both of these terms. So by algebra, you can factor out the 250 squared and then move it outside of the square root. So it's no longer a 250 squared, it's just a 250. What's left under the square root is 4 squared plus 1 squared. 4 squared plus 1 squared, which is 250 square root of 17. I'm not tormenting you by asking you to work through that because I think it's kind of counterproductive, but this is the sort of problem that appears on the AP Calculus exam, so be that as it may. Okay, so knowing that this is, I'll put the meters back in. Knowing that this is d, what should I write next for d dot at time t equals 5 seconds?
So we are going to see that. I assume we can say, wait, no, never mind. We can't just say unrelated. Anyway, so you can see that this is going to be also equal to 10 times 25 seconds squared times...
I'm dropping units. Okay, 10 times 25.
Wait, do you not need to specify seconds squared?
You do, but I'm being lazy because the way that this problem was stated was that the distance at time t is 10t squared meters. So by this equation, since the answer is in meters, when you plug into this equation, you don't need to include the units of seconds, right? Because it gives you an answer already in meters. So I'm just going to drop the seconds, because in principle this equation should have had an inverse second squared to cancel, but we're being a little sloppy with the units.
Okay. Let's see. And it's going to be times 100. Well, 100 seconds. You're dropping units.
Good. And then over d.
And this is all over 250 root 17.
Good.
Yeah. Cancel. 10 times 25 equals 250, so this 100 over 17.
Very nice. So d dot should be, assuming we have made no errors, 100 over root 17, and now I'll put the units back in at the end, because we know d dot is a rate of change of d, which is a distance, so it has units of length, rate of change of length with respect to time, so the units must be meters per second. Okay, good. This is very common, by the way, when I actually solve problems in real life, is that in intermediate steps I'll just stop writing all of the units because it irritates me, and then I'll put them back in at the end, knowing what the answer's units have to be. I don't know if that's a good or a bad thing. Often in high school problems it's useful to write the units in all the intermediate steps, but I don't really have the patience for this. So, good. Thoughts or questions on this answer?
Well, suddenly I'm curious, because would that second squared have impacted things?
Well, it would not have impacted things if this problem were posed in a sensible way. So I copied this verbatim, by the way, from the AOPS book. What they should have said, if they were being careful about units, is that, let's see, at time t, the rocket has achieved this altitude of 10t squared meters. What they really should have said is the rocket has obtained altitude 10t squared times meters per second squared at time t. Why should they have said this? Because if they had said this, then this means that if you plug in a particular choice of time, like 5 seconds, then in this equation you would have 10 times 5 seconds squared, and the second squared in the denominator would cancel. So you would get an answer for the altitude, which is in units of meters. That's what they should have said. Instead, they said something else which is technically correct, although in a very annoying way, because what they said in the AOPS book was at time t seconds. When you say time t seconds, that means that the variable t has no units, right? If you say time t, that's different. Time t means t is a variable with units of seconds. If you say time t seconds, that means t is a variable with no units, right? Like t equals 5 means 5 seconds, but the seconds appear here in the paragraph instead of being attached to the variable t. So they did something a little sneaky. In physics problems, you tend not to do this. You tend to allow the units to be attached to the variables themselves instead of appearing in the paragraph, which is kind of annoying. So it's kind of a tangent, but what they said is technically correct, because we should not put in the seconds squared for t, because by definition t does not have units of seconds in the way they phrase the problem. But writing a time which does not have units of seconds is a bit bitchy. If I were writing the problem for physics students, I would have deleted this word seconds right here, so that t does have units of seconds, and then you would need to divide out those units later. Anyway, sorry, that's a bit of a diatribe, but is that what you were asking about, the second stuff?
Yeah, that makes more sense. It just didn't seem right.
Yeah, I agree. It's annoying the way it's posed, but still technically correct. Good. Other thoughts?
I have no other thoughts.
Okay. Let's do another problem like this, but first the solution. Hope we got the right thing. Aha, yes. So the way I solved it before was to write Pythagoras in terms of y, where I didn't plug in the value of y in terms of time. So at any value y, as you told me, we can differentiate both sides and get this 2dd dot equals 2yy dot, where before you gave me the actual expressions for y and y dot in terms of t. Then I plug in t equals 5. Again, here's the unit fuckery again, because the way they defined it, t equals 5 has no dimensions. It's not t equals 5 seconds, it's just t equals 5, because they were being sneaky. But at time t equals 5, we have this value of y in meters, given the equation. This is this 250 root 17 we found a moment ago. And therefore, if you plug into the equation we found by differentiating, you get this thing, which has the solution d dot is 100 over root 17 meters per second, which is correct. Okay, so it sounds like our arithmetic worked out, which is nice. Here's another classic problem. I don't know why calculus problems so often involve ladders, carrying ladders around a corner or ladders sliding down a wall, but in this problem we have this ladder with a fixed length 10 feet, which is resting against a wall. So you lean the ladder against the wall, and then eventually the ladder starts to slide. So maybe at, I should draw that more diagonally, at a later time maybe the 10-foot long ladder looks like this, and then it's slipping so that at a later time, at a later time it's getting more and more horizontal. So slowly the altitude, the height of the ladder is decreasing, and it's getting, flatter as it slides down the wall. So while the ladder is executing this motion, we would like to find a relationship between the rates of change of, say, the height and the horizontal distance. So again, I will flag an annoying thing. We are given the length of the ladder in feet, and then we're told to consider a time at which the foot of the ladder is slipping away at a rate of 1 inch per second. So feet and inches are different, annoyingly. And then instead of being given a particular time, like t equals 5, which we had in the previous problem, now we're given a moment where the ladder forms a 60-degree angle with the ground. So it's slightly different. But Anyway, we'll cross those bridges as we come to them. So first, I will ask you to, assign some letters, assign variables to the various quantities in this problem that we're interested in, and then write or tell me how to write an equation which relates those variables. What should I do?
But before that, it doesn't seem like we actually have enough info here.
Interesting. Why do you say that?
We are not told how the degree has anything to do with how quick away. It's just slipping away constantly. So how does the degree matter at all?
So it's not slipping constantly.
Oh.
The slip rate can change, but we're told at a particular instant in time, the slip rate is 1 inch per second, right?
Okay. I see, because like a shorter lateral would fall faster.
Well, maybe, yeah. The problem's kind of contrived, so I don't know if that's true in general, but if assume that's true for here, I guess.
Okay, so thinking. What was the question again? I apologize.
Well, the question is very open-ended. I was basically asking what should I do next, right? So in the rocket problem, I tried to assign some variables for you, right? Like I wrote this and said call this D, and this was 1,000, and this could be, I don't know, Y, which happened to be 10t squared. So I assigned some letters to the quantities involved in the problem, and then asked you to take a derivative. My question this time was more open-ended. I'm not telling you what letters to assign to things. I was asking you, what should we label the quantities in this problem, and what equation should we write down to relate them?
I believe that we can start by placing on the bottom theta, theta equals 60 for clarity.
Okay.
And I guess we can assign h to the vertical height and L to horizontal height.
Okay, h of t, and you say horizontal should be L?
Yeah.
Okay, so can we write down an equation which relates some of the variables that you just gave me?
I'm doing some SOHCAHTOA stuff over here.
Yeah, this is a fun problem. You can either write down an equation using trig, so you use some SOHCAHTOA with theta, or we could do it using Pythagoras, which tells us about the 10-foot, the L, and the H. Right, so there's a couple options. Any of them work.
I'm going to try a method this time, just because we did Pythagoras before. Let tangent of 60 degrees equal h of t over L of t? Well, h over L.
I'm going to put theta instead of 60, because theta can change in time, right?
Right.
So we'll have to chain rule. It's not going to just be a constant, but we'll plug in theta equals 60 at the end. So good. As you say, tan theta is h over L. With, h of t, but I'm not going to write that. Good. Okay, so now we take derivatives. What do I get when I take derivatives in this equation?
So we are going to have to refer to the quotient rule. Remember? So this is going to be h dot L minus HL dot all over, attempting to remember, HL, no, just L. Okay, yeah, you're for me, thank you.
I thought you were going to say it before I finished writing it, but my bet did not pay off there. Okay.
Thank you.
Right side looks good. What about derivative of tangent of theta of t?
Trying to remember, we can just rederive it on the side. I can't remember. Overleaf takes forever to load. Tangent equals sine over cosine, to my knowledge.
Yeah, so tan sine over cosine.
Okay.
Then we ddx that guy, or dd theta that guy.
dd theta, let's see. Trying to remember. The derivative of sine is equal to cosine, so we're going to have cos squared theta minus, time to remember, negative, it's going to, negative sine squared theta. So it's going to be a overall plus sine theta squared all over cosine squared. And I believe we can split this into two fractions. So on the left side, it becomes tangent squared.
The left side. Well, let's see. The top, I mean, by Pythagoras, the top should be 1, right?
Oh, yeah, that makes much more sense. So,
squared, cosine squared, right?
Cos squared.
Right, but I think, wait, is this right? This would be 1 over cos squared theta, which would be the same as, what is this, secant squared theta? Is this correct? I thought
that makes perfect sense.
Let's see, is this, so, hold on, let me remind myself. So if we quotient rule this, we have derivative of the top times the bottom left alone, so that's cosine times cosine is cosine squared, indeed, minus the derivative of the bottom, which is derivative of cosine is minus sine, times the top left alone, which is sine. So minus sine times sine is plus sine squared, over the bottom squared. Sine squared plus cosine squared equals 1. 1 over cosine squared equals secant squared. I guess this seems right to me. For some reason I thought the derivative of tangent was secant theta tangent theta rather than secant squared.
D3, it is secant squared.
It is secant squared, okay, good. Why did I think that?
The derivative of secant is secant tan.
Ah, so I was confusing tan with secant. Okay, good. So you have corrected me. Good, good, good. So this is secant squared theta. Alright.
Yep. Did we need to chain rule the inside of that or anything?
Yes, so the chain rule with the inside would give us a theta dot, right? D theta dt.
Right. Lovely. Let's make it more complicated. Now we need to solve for this in the terms of something.
Yeah, so we know theta at the given time. So we know theta is 60 degrees. Can we figure out this stuff on the right? This is going to be more complicated. So I'll put in, at the time we know, theta dot times, well, secant squared is 1 over cosine squared. Cosine of 60 degrees is root 3 over 2, right? So secant of 60 degrees is 2 over root 3, which means secant squared is, what, 4 over 3, I think? If I did that right. And apparently, well, I'm going to multiply both sides by L squared because that's easy. L is just 10 feet, so that's not a big deal. H dot, what's H dot? That's what we're trying to solve for, right? Because H dot is how fast is the top of the ladder sliding down. So H dot is what we want. That's fine. We know what L is, that's fine. Minus H L dot. What's L dot? Well, L dot is the change in the x, the horizontal, which we know is 1 inch per second. So I'm going to put in, I'll put in units for now and then probably suppress them later, but L dot is 1 inch per second. Okay, that looks good, I think, so far. Okay, so we're trying to solve for H dot. What do you think I should do next?
I believe that we should not forget about the over L squared.
Well, I multiplied by L squared to cancel that out, right?
Okay, I was confused. Sorry.
Good.
Let's see. Everything's breaking. That's lovely. It seems like we can just progress through this algebraically by moving the h times inches squared, well, h inches per second to the left side. and then dividing the entire thing by L.
Okay, so h inches per second. I'll put in the L squared, so L is 10 feet. I'm going to move everything into inches. So L squared, let's see, 10 feet in inches is 120 inches, right? 120 inches squared, so there's the L squared. We still have a theta dot and a 4/3. And then you say we divide by L, so we're left with an h dot on the right side. When we divide by L, I'm running out of space, but when we divide by L, we get this 120 inches again, which is going to cancel one factor of the 120 inches in the numerator. So
I am mildly confused. It looks like you moved the h inches per second to the left side, but wrote it down as multiplication.
good, that should be a plus. Good, good. Right, h inches per second plus, oh crap, so then, oh my god, that was not good. Oh lord. Can I undo that?
Done goof.
That's not good. Okay, let me be more careful. This should be first h inches per second plus this junk all divided by L. Oh, good. Okay, so that means we should write this in two terms. So I should not have canceled that square upstairs. So let me go back. And I was erasing this. Okay. Well, I don't want to cancel these. There we go. So when I make this a plus, this should really be h inches per second divided by 120 inches. And then in the second term, now we can cancel the 120 upstairs and downstairs, right? So that should be 120 inches times theta dot times 4/3. And that whole thing is equal to h dot. Okay, there we go. Is that, are you happy? Is this, does it seem copacetic so far?
This is all clear.
Good, okay. So the only thing we don't know now is theta dot. So what should I do to determine theta dot given the quantities at the time in question?
We could go way back and say that, okay, you're erasing it, no knows.
Well, I mean, this is just intermediate steps, but we can rewrite any of these as we need them. Okay, so way back to what?
To the, trying to remember, when we took the tangent of, not tangent, well, almost tangent, when we took the derivative of tangent, oh, I guess it was tangent.
Derivative
I'm
tan
very
theta?
confusing myself.
The tan theta is h over L stuff? That's thing?
Yeah, and that resulted in theta dot secant squared stuff. I believe that we could divide by secant squared on each side. Well, secant squared theta on each side and get an equation. But that might be unnecessarily complicating it. Yeah, it definitely is.
Yeah, I think that's hard because on the right side of this equation we had to quotient rule, right? So we had h dot L minus L dot h over L squared, which is hard because the thing we're trying to solve for is h dot, right? We don't know what h dot is. So maybe it would be easier if we could write down an equation which involves theta and whose derivatives involve only quantities that we know, right? So we know L dot, right? We know L dot at the time in question is 1 inch per second. So can you write down an equation that involves only theta and L and constants that we can differentiate and use to figure out theta dot?
Cosine theta equals L over 10.
Good. So the derivative of this is what?
This is going to equal to, give me a second, L dot Well, that doesn't even matter because 10 feet is constant. Negative of L, the derivative of 10 feet. Which, wait, no. Excuse me. Yeah, L dot 10. Negative L dot 10 over 10 feet squared.
Let's see. So on the right side, so we're differentiating with respect to time, right? So L dot over 10 feet, because 10 feet is constant on the right side. And then on the left, what's the derivative of cosine theta with respect to time?
The derivative of cosine theta is going to be recalling negative sine theta.
Yeah, so minus sine theta, theta dot, is L dot over 10 feet. Okay, so when theta is 60 degrees, what do I get for... Oh, did I do this wrong? I think I made an algebraic mistake. Did I say... this was supposed to be... Where did this come from? This was supposed to be secant squared theta, right? Did I say something wrong? Because derivative of tangent you said was secant squared, which is 1 over cosine squared theta. Cosine of 60 is a half. Oh, so I made a mistake. I said cosine of 60 is root 3 over 2, but that's sine 60. Why did I do that? So, sorry, I think the equation we wrote down was wrong. This should be a half squared, which I think is a fourth. I don't know why I just noticed that, but anyway, so coming back to the equation at hand, so when we plug in the time in question, is when the angle is 60 degrees and when L dot is 1 inch per second, what does the equation that you've just given me reduce to in that case?
Desperately trying to remember things. So there's going to be 1 inch per second over 10 feet. Well, 1 inch per second over 10 feet divided by negative 3 root 2. Excuse me, negative 3 over root 2.
3 root 2, and then you say
Yep,
solve.
I'm confusion.
Let me convert units, so this works out to 1 inch per second over, let's see, 12 feet in an inch means 120 inches. And then as you say, we should solve for theta dot, which means there should be a root 3 downstairs and a 2 upstairs. So theta dot should be minus, let's see, 1, the 2 cancels to give us, what, a 60? 60 root 3, is this right? Am I doing this right? So the 2's give us a 60 and there's a root 3 downstairs per second. Does that look right?
Thinking. Yeah.
I think that's right. Yeah, I mean, as you told me, sine 60 should be root 3 over 2, so that part's right. The right side is correct after converting units to 1 over 120. Multiply both sides by 2. 2 over 120 is 1 over 60. Divide both sides by root 3, so there's a 1 over root 3. And the minus sign gives us this. So I think, I mean, why did I write seconds? Inverse seconds. I think that's right. Okay, so we're almost done. We know theta dot, because we've just solved for it. We're trying to get an equation for h dot, which means we need one more thing. We need h. So at the time in question, let me redraw the ladder, the triangle. At the time in question, this is a 60-degree angle, and this is a 30-degree angle, and the hypotenuse is 10 feet. And to plug in to the left side of the equation you gave me, we need to know what h is, which means at this point in time, we need to know what is the height h, the vertical extent of this triangle. So how do we find that given the information in the leftmost diagram?
Sine 60 equals h over 10, or Just, let me think. 10 root 3 over 2 is the length of h.
Good. So h is 10 times root 3 over 2, which is what, 5 root 3 feet or something? Which, because of the annoyingness of this problem, is what, 60 root 3 inches if I multiply by 12? Kind of a pain. Okay, so if we've done everything correct so far, which I'm starting to doubt, let's see, h dot should be h, which is 60 root 3 all over 120. Inches cancel. I'm going to write the units in a moment. Plus 120 over 4 is what, 30? Times theta dot, which we computed as minus 1 over 60 root 3. Minus 1 over 60 root 3. This is all supposed to be, we're missing some units, aren't we? This whole thing should be, oh, why did I write inches here? Yeah, that's why. Ah, damn it. There we go. I wrote inches here when I shouldn't have. There we go. So this should all be inches per second, I think, should be the units. This is what happens when you switch between suppressing and not suppressing your units. So you get weird stuff. So if we have been very fortuitous, then the result should be h dot equals, well, 60 over 120 is a half. So root 3 over 2. And then 30 over 60 gives us a minus 1 over 2 root 3, all inches per second. How do I simplify this now? Well, I could get a common denominator, I guess, multiply the first factor by root 3 top and bottom, which would give 3 over 2 root 3. 3, damn it. 3 over 2 root 3 inches per second. Do you agree with that so far? Multiplying root 3 top and bottom? Is that okay?
Yeah.
Okay. So then if that's good, then we can do 3 minus 1 is 2. 2 over 2 root 3 is 1 over root 3. Something's wrong. Why is the sign wrong? Somewhere we dropped a sign here. That should be, well, what we found was 1 over root 3 inches per second. Something seems wrong because the height is the, vertical extent of the ladder. So if this thing is sliding down, I think the answer for h dot should be negative, right? The answer for h dot should be negative since this thing is getting shorter. It's decreasing in height. So do you see where I dropped a minus sign somewhere? I think somewhere I dropped a minus.
Well, it says sliding down. If it was sliding up, then it would be negative. I mean, if it was sliding up when it was being called sliding down.
But I mean, the answer we get should have a minus sign. The fact that it's sliding down should be reflected in our answer, right? I mean, the way that we've defined the quantities in this problem, h is this vertical height and L is this horizontal distance. So L dot should be positive and H dot should be negative, right? That's not something that you can just point to the problem
Now I
and
see.
right? Yeah.
Yeah.
So we made a mistake somewhere. H dot minus 2 root 3. Where did this... I've already erased enough now. Where did this top equation come from? This thing must have had a minus sign that we dropped. H dot This thing came from the, what was it, tan theta was supposed to be h over L, right? That's where we got this from, which meant, are we sure the derivative of tangent is secant squared and not minus secant squared? Yeah, I guess that must be right. Tangent gives secant squared theta. Theta dot is h dot L minus LH dot over L squared, and we solve that. We get L squared secant squared theta theta dot plus L, or sorry, oh, is that what it is? No, no, that's not right. This should be L dot minus L dot H. So this looks right. What did we do?
If our number matches, but it's of the wrong sign, could we say that we
Could we say that what? Sorry, you cut out.
loud noises, of course? Are you joking me, Discord? This is why I use push to talk.
What was the end of your sentence? I heard if the number matches, but our sign is wrong, then, and then you cut out.
If our number is correct, but the sign is incorrect, could we just say that there was a global negative that we...
Well, no, that's inconsistent with the definitions we made at the beginning, right? We defined at the beginning h of t is vertical, which means that h of t gets more positive the higher the ladder is. So, I mean, we can't just change our minds about the definitions because we decided on those on step 1, right?
I feel like my sentence got cut off again.
Ah, okay. What was the rest of the sentence?
Much better. Actually, maybe my sentence did come across and it's just not the answer I expected. It doesn't seem like your response matched what I said, so as I was saying, could we have the incorrect... I don't know. I'm just saying, could we say that it was good enough?
I mean, no,
Never good
I mean,
enough.
it's wrong. If the sign is wrong, it's wrong. It's a small algebra error somewhere, but you can't just say the sign is wrong, so that's good enough. Trying to understand where we made the mistake, because the way I solved it was with Pythagoras. Let me just hide and see. Maybe looking at my solution will help us see where we made the mistake. So if you solve it with Pythagoras, it's only a couple steps. So I called them x and y instead of L and h. So x squared plus y squared is 10 feet quantity squared, which is 100 feet squared. Differentiate and get 2xx dot plus 2yy dot is 0. Then we use this 30, 60, 90 argument again, which means x at the time of interest is 5 feet and y is 5 root 3. So we found this. We found y, which I think you called h, was 5 root 3 at the time of interest. We plug that in, but when we solve with this technique, you get a minus sign. Y is minus 1 over root 3 in inches per second. So that's manifestly the correct answer because it should be negative. If you define y to be the height of the ladder, your answer must be negative if it is to be correct. Right? That's non-negotiable. It has to be a minus sign. So what did we do wrong here when we wrote tan theta as h over L, differentiated to get secant squared theta theta dot equals h dot L minus L dot h over L squared, which means h dot equals, let's see, L secant squared theta theta dot over L which is secant squared theta theta dot, plus L dot H over L. This seems all right. Somewhere there's just a small algebra error, which made us get plus 1 over root 3 instead of minus 1 over root 3. What did I do? Well, it seems very close. Maybe I'll need to uh, rely on this thinking about it more and discussing next time and having another errata slide to think of what we did wrong and correcting it, which I hesitate to do because I don't want to make mistakes every time we talk, because then I fear for wasting your time. But it seems like we're very close. Somewhere there was just a small error, and we almost had the correct answer up to a sign. But I don't know. Do you see anything where we did something sketchy or might have made a mistake?
I keep forgetting I pushed the top one. Okay, so the screen is filled with algebra, so good luck finding it.
I mean, I'm going to take a screenshot now.
I forget what I was thinking. Are you recording? You might be able to review the footage.
Yeah, I will watch the footage, and I will also watch the screen share, and if this is anything like last time, I'm going to quit the call, like, go for a walk or collect my thoughts and, like, cry for, like, 5 minutes, and then look at the problem again and realize it was really easy, and there was an obvious mistake somewhere that I, for some reason, missed in the moment. So I suspect it's something very easy, which is why I'm pausing now, because I was just kind of hoping that I would find the easy error in the moment, but I don't know. I still cannot see it, so I might have to review and tell you what I think it is next time. But
No
okay.
problem with that.
Okay, I apologize. Modulo the sign error. Any other thoughts or comments? Fucker. About this
I
question?
have nope, no further thought.
Okay, so we have a short third act to go through, and I will post problems about related rates, quote unquote, like the ladder sliding and things like that next time. Well, probably tonight. But this stuff we will do more next time. I would just like to motivate what we're trying to do this time as a teaser. So what is the motivation for what we're doing with L'Hopital's rule? This is another application of derivatives. We've been seeing ways of using differentiation to get extra data about various systems like graphs. So we found critical points, for instance, places where the derivative is 0. Using differentiation and using some of our theorems, we've studied convexity and concavity, whether a graph is concave up or concave down using the second derivative. One more use of derivatives that we'll use in this chapter will relate to computations of limits which were too hard for us to do before. So what do I mean by too hard before? When we computed limits in chapter 2, we only had a very small toolkit of ways to evaluate those limits, right? In some cases, we used a direct epsilon delta argument for, say, stars over Babylon or something like that. And this was kind of challenging to write out, but this gave us answers in a few simple cases. Our second way of doing this was using the squeeze theorem. So this is, for instance, how we proved that the limit as x goes to 0 of sine x over x, I think we proved this is 1, using the squeeze theorem with this triangle area argument that we had before. And the third way that we had was using these theorems. So we proved various theorems about the limit of a sum or a product or a quotient, and then we used those theorems to prove very powerful properties, like for any polynomial p of x, so p of x polynomial, we use these to prove that the limit as x goes to a of any polynomial p of x is the same as p of a. And that's what we used to argue that polynomials are continuous. So that was really nice, but that only applies in, that third case, so we're really limited to these three types of limiting calculations. No pun intended. We're limited, or we're constrained, perhaps a better word, to only solve limit problems in these three situations. So what if we had a more complicated limit, like this limit as x goes to 1 of x squared minus 1 over log x? So it's very hard to use the results about the theorems for limits of sums, products, and quotients here, because as you can see, this thing doesn't satisfy nice continuity results. The top and bottom tend to 1 squared minus 1 over log of 1, and that means the numerator goes to 0. We know log of 1 is 0, so this thing tends to 0 over 0, which is not very well defined. So we cannot apply our theorems in case 3 to this case. One could do a direct epsilon delta argument to this function, but as you can kind of tell, it's going to be pretty hairy. It's complicated to write down epsilons and deltas that involve a quotient like this. So although it can be done, it's probably more work than is necessary. And it would require a lot of ingenuity to pick two functions, say f and h, which upper bound and lower bound this function, just because its form is so complicated. So it would be nice if we had another way of computing limits that did not rely on any of those three techniques that would be able to apply more broadly. Good, so that's the motivation for the next part of what we're trying to develop. We're going to try to develop a technique to evaluate limits like this, but it will necessitate an intermediate theorem before we can actually prove the result that we want. But good, so thoughts on the motivation before we prove the intermediate theorem?
I do not believe I have any thoughts, ideas, or questions. Ideas. Good job, Sal.
Ah, dear. You sounded hesitant, though. Does that mean you might have a thought, but you're afraid to say it, or you're not sure whether you have thoughts?
I don't have any thoughts.
Okay. You said it more confidently that way, so now I'm happy. Good, okay. What is the intermediate result, then? So we're going to prove something first, which seems unrelated to this, but which will help us. So this is called the Cauchy mean value theorem. So I will explain why. I mean, it's named after, I forget his first name, Cauchy, famous mathematician. I'll explain how this is related to the usual mean value theorem in a moment. But first, the statement of the theorem. So we have two functions, f and g. We assume both functions f and g are continuous on the closed interval a to b and differentiable on the open interval a to b. So you may recognize these are the same assumptions as in the usual mean value theorem. That's one similarity. Now the conclusion of the theorem is that there exists a number x in the open interval from a to b with the property that this equation holds. What is the equation? Quantity f of b minus f of a times g prime equals quantity g of b minus g of a times f prime. Okay, so this looks very mysterious. What does this equation mean? But again, I'll come back and interpret this in a moment. First, the proof. The proof uses a very common technique we've seen a few times now. When you want to prove two things are equal, it's easier to define a function which gives their difference and try to find a place where either that function or its derivative equals 0. So in this case, we'll use the second technique. We define a function with the property that when that function's derivative equals 0, this equation will be true. So what do I mean by that? We define a function h of x, which is f of x times g of b minus g of a, minus g of x times f of b minus f of a. And you can see by differentiating that h prime is f prime times g of b minus g of a minus g prime times f of b minus f of a. So when h prime equals 0, this equation is satisfied. So it's just a hack. We're defining a new function to make life easier, because now we just have to show there's a place where h prime equals 0. It's just a trick. Okay, so how do we show that there's a place where h prime equals 0? We're going to cheat and use something we proved before, which is Raleigh's theorem. So the hypotheses of Raleigh's theorem were that h is continuous on a to b, differentiable on a to b. We assumed both of those. And finally, it had to satisfy h of a equals h of b. So remember, this was pictorially the claim that if you end up where you started, so if this is a and this is b, and h of a equals h of b, which means you end where you started, then there had to be a place where you turned around. That means there had to be a place where the derivative h prime equals 0. And that's exactly what we're trying to prove, right? We're trying to find a place where h prime equals 0, so Raleigh's theorem sounds very useful. But first, a challenge for you. What about this last claim that h of a equals h of b? So can you check this or tell me the algebra I should write down in order to verify that h of a is the same as h of b?
All right, just by inserting.
Inserting 5,000 times, but go on.
Inserting a. Let's see. Inserting a into all occurrences of x.
Good.
Okay, let's see. We get something along the lines of equals f of a times f of a times g of b minus g of a, and parentheses minus g of a times f of b minus f of a. I think I have an idea what's going on, but I'm just writing it all. Well, I'm asking you to write it all out.
Good, so I think we have some cancellations now. So when we distribute each of these, what do we get on the next line?
Okay, so we're going to have this water. Why does it exist? It's not even raining. Okay, just gonna go down the line. F of a times g of b minus f of a times g of a minus begin parenthesis.
Well, distribute this too. No parentheses, right?
Well, because it's all multiplying by that negative.
Oh, so you mean minus in parentheses like this?
Yeah, just to make it easier to look at. Okay. Time. It's going to be g of a times f of b minus g of a times f of a.
Minus g of a, f of a. Okay, that looks good. What cancels now?
I believe that the f of a and g of a cancel.
Good.
No. Yes. Yes, they do.
Yeah, this is a minus, and this is a minus minus, which is a plus. So those both cancel, as you say. And we are left with f of a, g of b, minus g of a, f of b. Okay, so now we just have to check that that's the same as h of b. Okay, so I will erase the work but leave the result, and then we'll just compute h of b and check whether the result matches. Okay, so what's h of b doing the same stuff?
Doing the exact same stuff, substituting b for x. Let's see. This is going to be f of b times g of b minus g of a minus g of b times f of b minus f of a.
Good. Okay, and simplifying that gives us what?
FBGB times, FBG FBGA. Well, yeah, that's right.
Okay.
Minus begin parenthesis GB FB minus.
Wait, did you cut out, or is it push to talk fucking up again?
It's going to be GBFA.
Ah, good. Okay. Sorry, there was a Momentary interruption. Okay, sounds good. Then sounds like the same thing happens where this, let's see, we have an, let's see, f of b, g of a, and an f of b, g of b, and a minus f of b, g of b. So this time it seems like these terms cancel, right? The first one's positive. F of b, g of b is the same as a minus g of b, f of b. So we're left with, what's this, minus f of b, g of a. And then here we have minus minus is a plus, plus g of b, f of a. So now we're in good shape because we were trying to prove that these two were the same, but now we see that actually the two terms match. I've written them in a different order, but yellow? Yeah, yellow. So these two are the same because the first term up here is minus f of b g of a, and the second term down here is minus g of a f of b. So that's the same thing written in a different order, right? Multiplication is commutative, for numbers at least, not for matrices or group elements. But those two are the same, and the second term of the first line is the same as the first term of the second line, right? Plus g of b f of a is plus f of a g of b, so you can switch the order. So it sounds like that claim is on solid ground, but questions or concerns about this claim?
I have no questions or concerns.
Okay. Apologies for subjecting you to algebra then, but hopefully it was worthwhile to check this. So, good. Now we know that the function we defined, h, satisfies this condition where you end where you started, right? H of a equals h of b. And it satisfies the other assumptions in Raleigh's theorem, which means the conclusion of Raleigh's theorem must also be true, which is to say there exists a point where you turn around, right? There is some x in the open interval a to b where h prime of x equals 0. But this is pretty easy to differentiate. My favorite type of equation to differentiate is the one where you just put primes in, because everything else is a constant. Right, this is a constant, so I don't have to worry about that. This is a constant, so I don't have to worry about that. Therefore, the derivative of h is simply h prime equals f prime times this chunk minus g prime times this chunk. So if we know there's a point x where this thing equals 0, then that means by adding the second term, the minus, the negative term, to both sides, that implies that there exists a point x where f prime of x times g of b minus g of a equals g prime of x times f of b minus f of a, just added to both sides. So we know there exists an x such that this is true, but that's exactly what we wanted to prove, right? That was the statement of the theorem's conclusion. So by Raleigh's theorem, we have found a point x where the conclusion we wanted to show is true. So we're done. Okay, thoughts on the proof before I explain why it's called the Cauchy mean value theorem?
I have no questions on the proof.
Okay, good. It's not a bad proof. Okay, so why is this called a mean value theorem? Let's pick a special case, right? This holds for any function f and any function g. So let's pick the simplest function g, which is not trivial, that you can think of, which is just g of x equals x, right? So g takes in a number and spits out the same number. If that's true, then this equation we've written down reduces to the following. On the left side, well, g prime is 1, right? Because the derivative of a line with slope 1 is simply 1. So the left side is f of b minus f of a. The right side, well, g of b is b, because g takes in a number and spits out the same number. So g of b is b, g of a is a, and f prime, well, that's still f prime. That means we can solve for f prime and find f prime of x equals f of b minus f of a over b minus a. And we shouldn't forget what the theorem is telling us. It's telling us there exists an x such that this is true. So now you might be seeing why we call this a mean value theorem, because the ordinary mean value theorem told us that on any interval there exists some x. That means there's at least one point on that interval with the property that the tangent line slope at that point equals the secant line slope on the interval. That was the regular mean value theorem. Now we have proved a more powerful, a stronger theorem that involves a function g, but we see that in the special case, when we replace g of x by x, this theorem tells us, again, that there exists a point x where the tangent line slope equals the secant line slope. So we call this the Cauchy mean value theorem because this is a generalization of the ordinary mean value theorem, where now it's not just any function x that you can plug in to get a relationship between the tangent line slope and the secant line slope. You can put in whatever function g you want, and you still can find a number x. You can still prove there exists a point x where this equation is true. So it's a stronger result. It implies the mean value theorem, but also implies, other results different from the mean value theorem. Okay, does that make sense? Questions on this?
I have no thoughts or questions.
Okay, very good. So I will end on this. This is what we will prove next time, but it was the motivation for developing this theorem. So this is a very powerful theorem called L'Hopital's rule. What's the statement of the theorem? So the theorem is this. Suppose you have two functions f and g, and you know that both of those functions go to 0 at some point. So the limit as x goes to a of f equals 0, and the limit as x goes to a of g equals 0. So for instance, this could be like that function we were looking at back here, like f is the numerator, x squared minus 1, and g is the denominator, log x, because both of those go to 0 when x goes to 1. So we have two functions that go to 0 at some place. Okay, great, fine. So you have two functions which go to 0 at some place. Suppose that the limit of the quotient of their derivatives exists. You have to assume this limit exists explicitly. But if you assume that that limit of the quotient of their derivatives exists, then it's also true that the limit of the quotient of the functions, not their derivatives, the functions themselves, also exists. And more surprisingly, those two things are equal. The limit of the quotient of the functions is the same as the limit of the quotient of the derivatives. That's very weird to me. Usually when we have a quotient of functions, you would expect the quotient rule to enter, right? You would expect something involving f prime g minus g prime f over g squared. That is not what enters here. What enters in this theorem is literally the derivative of the top divided by the derivative of the bottom. F over g approaches the same point as f prime over g prime. So, I find this remarkable. We'll prove it next time, but I would just like to explain why this is powerful. Because remember, back in chapter 2, we had to play these really kind of circular and difficult games, circuitous games, involving the squeeze theorem to prove that the limit as x goes to 0 of sine x over x equals 1. Right? We had to prove the squeeze theorem, or prove using the squeeze theorem that this is true. Once we have L'Hopital's rule, there's a much easier way to prove this. You just look at the left side and say, well, top and bottom go to 0. Sine of 0 is 0, and x at x equals 0 is 0. So by L'Hopital, I'll just write L apostrophe, by L'Hopital, this is the same as the limit as x goes to 0 of the quotient of the derivatives. So what's the derivative of sine? Well, that's cosine. What's the derivative of x? Well, that's 1. And now we don't have any problem because this is continuous. So you can plug in cosine of 0 is 1. So you're done in one step. You don't have to use the squeeze theorem. You just take the derivative of the top and bottom, and it's much faster. Same thing with this other thing you did on a consolidation document problem. This cosine x minus 1 over x, you still had to use the squeeze theorem, and it was a pain in the ass. But once we have proven L'Hopital's rule, you could just say, well, top goes to 0, because cosine 0 minus 1 is 0. Bottom goes to 0 because x, at x equals 0 equals 0. So differentiate top and bottom. Top you get minus sine x minus 0 because this is a constant. Bottom you get 1. And the limit as x goes to 0 of minus sine x equals 0. So it's much faster. It's very easy to prove limiting results using L'Hopital's rule. Okay, but we're almost out of time, so I will not prove that this time. Next time, in addition to the errata about that minus sign in the falling ladder, I will also prove L'Hopital's rule, and then we'll do some more problems because this is the last major topic in Chapter 4. So that's the punchline for today. Other thoughts or questions on this teaser slide?
I have none.
Good.
When is next meeting?
Should be next Monday, right? We're back on the Monday-Thursday schedule? Are you free next Monday?
Yeah, I'm always free. Because I kind of dedicated it.
Okay, that's good. I mean, it's okay if you're not.